Okay, you guys, so this third video is going to discuss method number 3 regarding alpha alkylation, and this will be our last method. And this last third method is known as SAMP and RAMP chemistry. And it was pioneered by E.J. Corey at Harvard. E.J. Corey is known as one of the grandfathers of organic chemistry. He won the Nobel Prize for total synthesis and how to approach a total synthesis. And he did this work with his postdoc, Dieter Enders. And so even though they pioneered the work and Dieter Enders was a postdoc at the time, Professor Enders made it his career. So really a lot of the work comes from Professor Enders' research. They first published this in 1976. So before Evans oxazolidinones, before Andy Myers, they published it in a Tetlet paper. Tetlet means tetrahedron letters. 1976. And it's a pretty short read. It's not the most popular method. It is limited, but the beauty of it is that just like your Evans oxazolidinones and your Andy Meyer pseudoephedrins, the molecules used are all derived from either natural resources or cheap resources. And so these are the two molecules. The first one is known as SAMP, and it stands for S1 amino 2 methoxy methyl pyrrolidine. Excuse me, pyrrolidine. So you can see S amino methoxy pyrrolidine, where the S stands, of course, for the only stereocenter present in the organic molecule, and this is RAMP. For our 1 amino 2 methoxy methyl pyrrolidine. Again, R stands for the stereocenter that's present in your molecule. These two are obviously enantiomers of each other. The SAMP molecule can be derived from S-proline amino acid, whereas the RAMP can be derived from glutamic acid amino acid. So really easy to make, really cheap. If you want to learn how to make them, please feel free to come to office hours. The Tetlet paper does cover it, but not as extensively. It's a really short synthesis, which is really nice. And so these two molecules can also be used for alpha alkylation and setting stereocenters, but they are very specific. And what I mean by that is that they're very specific in the sense that you can only use them for aldehydes and symmetrical ketones. And let me go ahead and highlight those. So you're limited on the type of carbonyl compounds that you can use them. So let me go ahead and introduce this. So how does this work? And I'll try to outline them and stay consistent with how I've been outlining the other two methods. The first thing is introducing SAMP or RAMP onto our carbonyl, which is our aldehyde or ketone. The beauty of this is that you've seen this before. So this will be hopefully a review. And again, this is specific to aldehydes and ketones. In Chem 124, your second semester, you learned, and I'll use an aldehyde, that in the presence of a primary amine, and an acid source, you always formed what's known as an imine. And this is again specific to aldehydes and ketones. Same thing occurs in this case. I am going to use the SAMP example, but of course this happens with RAMP as well. I'm going to use an aldehyde. Now, what I want you to note is that our SAMP molecule has two nitrogens, right? But this is the nitrogen that I care about. That's the nitrogen that's doing all the chemistry. That's the one that's got two protons that I can get rid of. And this is, of course, a primary amine. In the presence of an acid source that's a catalyst, you, of course, get an imine. And here is your imine. Please notice the similarities between the two, what you've learned in Chem 124 and what we're learning now. The mechanism is exactly the same as what you've learned in Chem 124. Under acidic conditions, you don't have any negative charges. So just a quick review of your mechanism. I usually tell my students, if you have an acid source, you should not have negative charges whatsoever. I will use sulfuric acid as my acid source and my catalyst. You always protonate your carbonyl. And you form your conjugate base. You keep track of your conjugate base because you need to regenerate it. Your acid always gets regenerated because it's a catalyst. So it always needs to be made. You now introduce your nucleophile, in this case, my SAMP molecule. This should be a review. So please make sure you're reviewing your lecture notes from sophomore organic chemistry. You now do a proton transfer. You need to get rid of your water molecule. Please notice that as I'm going along in my mechanism, there are no negative charges. The only negative charge that's present is my conjugate base. which makes sense because I'm going to have to bring it back and regenerate my acid catalyst. Additionally, this is not an organic molecule, right? So everything is either neutral or positively charged. I've got my great leaving group. I can kick it off. And of course, I form water as a byproduct. And you can start to see the precursor to my molecule. I finally come back with my conjugate base and I regenerate my acid and my desired amine. So all Chem 124. Feel free to stop by office hours if you need to review or if you need to ask me something about it. Pretty straightforward. Okay. So that's step one. Step one is to introduce my SAMP or my ramp onto my carbonyl compound, Chem 124. Step two. Just like with the Evans oxazolidinone and the Andy Myers chemistry, form enolate. Okay, I'm going to take the aldehyde that I just made. Excuse me, the imine that I just made from the aldehyde, and I'm going to treat it with LDA. Luckily for us, LDA, again, as we've mentioned in Chem 124, is the most popular base. It's the strongest base. It's the most commonly used. And it is going to deprotonate at the alpha position. I want to draw these hydrogens a little bit clearer for you. Okay. Just like before, you form your conjugate base. Now, if you remember for our Evans oxazolidinones, for our Andy Myers methodology, we always formed our conjugate base, and then we drew out the possible enolates. And we'll do that for this as well, because when you've got a resonance structure, just like before, there are two possible resonance structures. And so let's go ahead and draw those out. The first resonance structure I'll come back and finish the structure in a second. Just give me a minute. Okay. So a couple of things that I want to say. If you've noticed, I've drawn one of the structures with the R group on the same side as the nitrogen and the other R group on the opposite. But let me just finish up the first structure. And what I want to say is that in the presence of LDA, what ends up happening is that the lithium plus charge is floating around and it complexes, not surprisingly, to the N minus. Not only is this happening, but what ends up happening is it flips your SAMP molecule around 180 degrees. And the oxygen can also complex with the lithium. Okay. So you would expect for the lithium to just complex with the nitrogen, and that's it. But that's not the only thing that's happening, or that's not the only thing they suspect is happening. What they're also noticing is that the oxygen wants to complex to the lithium. And in order to do that, it has to flip from here to the top. And because it's flipping and rotating around the nitrogen-nitrogen bond, it is now dashed. It's not a reaction. It is literally just flipping 180 degrees. That's it. The same thing happens in the other possible resonance structure. And let me draw that out. Just like before, the lithium plus complexes to the N minus. Just like before, the methoxy group also wants to complex to the lithium, so it flips and rotates around the nitrogen-nitrogen bond, and it's forming a interaction between the oxygen and the lithium. So these are my two possible resonance structures. Not surprisingly, just like before, I cut my molecule in two. I prioritize my substituents on either side. My two substituents in this case are on the same phase. This is my Z enolate. For this case, my nitrogen, priority 1, R group, priority 1. This is my E enolate. You'll notice that for the Z enolate, if I have a bulky R group, I'm going to start noticing sterics, i.e. crowding. This is bad, and therefore unfavored. Hydrogens are small. There will never be, or there won't be significant sterics. So in this case, my E enolate is favored. So vastly different from what we've seen from Evans oxazolidinones, Andy Meyer's pseudoephedrins, where the Z enolate was always the one that was favored. For SAMP and RAM, it's the E enolate that's favored now. Okay? Okay, so again, please make sure that you notice this. This is probably one of the harder parts, is that when you deprotonate at the alpha position and you form your resonance structures, i.e. your E enolate and your Z enolate, you rotate because the methoxy group also wants to complex to the lithium that's already complexed to the nitrogen. This will always happen. This is forming a chelate, and we talked about the definition of a chelate. It's an organic molecule complexing to a metal. These are not bonds. These are just interactions, sort of like hydrogen bonding, right? Even though it's known as hydrogen bonding, it's really not a bond, it's an interaction, okay? Same thing here. A chelate is an interaction between these electronegative atoms and a metal. Okay, so now you've got your favored E enolate. Again, you have to see things three-dimensionally. So we move on to step 3. SAMP and RAMP chemistry is probably some of the hardest chemistry that you have to visualize three-dimensionally. And so step 3 is alpha alkylation. And now we have to look at things three-dimensionally. And so what I'll do is I'll do what I did before and redraw my enolate. Okay, so this is just from up here. This is my enolate, where my R group and my nitrogen are on opposite sides. This is where it gets tricky, and it's a little tedious to understand. This is my two-dimensional structure. I'm going to draw this three-dimensionally now. You won't be asked to draw it three-dimensionally on a quiz or on a midterm. I would never ask you. I'm introducing it to you so that you understand the stereochemistry that's resulting from this methodology. Okay, so again, I will not test you on this, but I'm introducing it so that you understand it and you're just not memorizing why things are happening. Okay, so drawing it three-dimensionally can be pretty tedious. And so let me go ahead and draw it down here. And what I'm going to do currently, it's on the plane of the page. I am going to flip it 90 degrees so that I'll call this carbon 1 and 2. So that now my hydrogen at carbon 1 is coming out towards you. And my R group at carbon 2 is coming out towards you. Okay. And so again, if you notice, I've flipped it 90 degrees on the plane of the page, and now the substituents H and R at 1 and 2 are coming out towards you. Okay. And then I get to draw the entire five-membered ring. And so just bear with me because it is a pretty tedious structure to draw. You're drawing your five-membered ring. Okay. Again, I'm not expecting you to draw it. I'm just drawing it for you so that you understand what's going on. Remember, it complexes to your lithium. And what they think is happening is it's forming this sort of five-membered ring, excuse me, six-membered ring transition state. And you can see I'm trying to draw this six-membered ring transition state. A couple of things that you should be noticing. The first thing is obviously the nitrogen is coupling to the lithium and the methoxy is coupling or chelating to the lithium. Just like in our two-dimensional drawing, it's dashed and facing down. It's facing down. Okay. So you're forming the six-membered transition state. Okay. Perfect. Now that we've got our six-membered transition state, now we move on to our alpha alkylation. It looks pretty overwhelming. So I'm going to try to remove the highlights. So that we're only focusing on the bonds. And that's it. Okay. I don't think I can remove those. So now I introduce my alkyl halide. Here's the thing. Your alkyl halide, if you remember, alkenes are flat. And alkyl halides can come in from the bottom or from the top. Okay? Bottom of your alkene or from the top of your alkene. The problem that's occurring from the top is that if it's coming in from the top, it is interacting with your five-membered ring. So unfortunately, your alkyl halide cannot come in from the top side. It has to come in from the bottom. Okay. And so because it comes in from the bottom, your R group is introduced from the bottom, which makes sense. So let's draw the product that arises from that. And I'm just going to draw, sorry, I'm just going to draw carbons 1 and 2. And what I want you to notice is the following. I'll call this R prime. So R prime came from the bottom, which means that my R group and my hydrogen are in a tripod facing up. Okay. And that's it. You're done. A couple of things that I want to say because I think this is probably the hardest to see of the three methodologies. Because you've started to form or regenerate your imine, you're no longer worried about wedges and dashes here. Your biggest concern is your wedges and your dashes on your alpha carbon, which is carbon number 2. Okay. The other thing is notice that typically the alkyl that you add is the one that's either wedged or dashed, right? This is just on the plane of the page. And that's perfectly fine. You can also rotate. And if you rotate, so that it does have a it does have a wedge or a dash to it, that means that your R group has to be on the plane of the page, forcing your R1 group or R prime group to be wedged. Now wedged. Okay. So you rotate about the carbon 1-2 bond just enough to make your R group on the plane of the page. Okay. Please notice that once you introduce your R prime or your alkyl group on there, it is syn. Or cis to the substituent on your SAMP molecule, on your SAMP organic molecule. Okay. So it shouldn't come as a surprise that if you start off with the ramp, you are going to see cis product relative to the substituent on your ramp organic molecule. Okay. So take home message, you always get the cis-syn product. I've just tried to explain to you why you get the cis-syn product. You get it because you form a three-dimensional structure with a six-membered ring transition state. Your alkyl halide can only be introduced opposite to your five-membered ring. And so in this case, because my five-membered ring, and I'm using SAMP, is facing up, then my alkyl halide has to come in from the bottom. If it comes in from the bottom, I can rotate things around so that now it's wedged and my R group is on the plane. Please notice that once my alkyl halide is introduced, my lithium no longer needs to complex to the nitrogen, right? It breaks that complex and it rotates back into place. The only reason the lithium is complexing to the nitrogen is because the nitrogen is negatively charged. Once it forms the imine and regenerates the imine, the lithium no longer complexes, and I no longer have this six-membered ring transition state chelate. Okay. Okay, so you will always get the cis-syn product. Not surprisingly, this works best for aldehydes and symmetrical ketones because if you had unsymmetrical ketones, then you would get a mixture of products because unsymmetrical ketones have two alpha sides, right? And if they have two alpha sides, then you are going to get different enolates and different alpha alkylations. Again, this is only for aldehydes and symmetrical ketones. This also works for rings, specifically ketone rings. Okay. And these can be slightly intimidating because you're so used to, or hopefully by now you're getting used to rotating things around your head, rotating things around carbon-carbon bonds in your head and moving molecules around. But rings can't rotate, right? The carbon-carbon bonds and rings can't rotate. So you're limited in what you can do. So let me go ahead and introduce the following. We'll talk about step 4, which is the removal of SAMP and RAMP in a second. I'll introduce SAMP. Just like before, you form your desired imine. I just want to use SAMP because I want to stay consistent with what we've been doing. Just like before, you treat this with LDA. So this is step 1. Step number 2, form your enolate. In this case, we really only have one alpha carbon. So despite the fact that it's an unsymmetrical ketone, you can't deprotonate here, right? Those are not acidic. You've only got one side to deprotonate from. And just like before, the minute you introduce LDA and you've got your negative charge nitrogen, The lithium complexes to your negatively charged nitrogen, rotates it around the nitrogen single bond. And my methoxy group also wants to bond to my lithium. Okay. Not surprisingly, you are only going to form the E-enolate when it comes to rings, right? Pretty straightforward. I can never form a Z-enolate with rings. The E-enolate will always be favored because rings are pretty set in place. You can't rotate around bonds. You're always only going to form the E-enolate. That's all there is to it. Okay. Now we have to draw this three-dimensionally. So I'm just going to redraw this three-dimensionally. Again, I will never ask you to draw this three-dimensionally. It is just to explain the stereochemistry that results from this reaction. This feels intimidating because, oh my God, Dr. Lucero, I'm going to have to draw a ring three-dimensionally. We're going to try to simplify this as best as we can. Just like before, this is on plane of the page. And what I'm going to do is I'm going to flip it 90 degrees, just like I did before. I'll label these carbons 1 and 2. You can follow along with the previous example. I'm going to draw my double bond just like I did before. What I'll do in this case is instead of drawing this ring, I'll just call this R2 and R1 and add a little curve to indicate that it's a ring. So I've highlighted yellow. Okay. And it's coming out towards you, right? Because it's flat. And then I'll do the rest of my molecule, which is my nitrogen system we've drawn before. You remember, I complex this to the lithium. And my methoxy group also wants to complex to my lithium. And there's my six-membered ring, just like we did before. Okay. The only difference from this structure and the one we drew is, of course, the ring side of my molecule. Just like before, I have to introduce my alkyl halide. I'll call this R3 so we can differentiate it from the ring. If you remember, it cannot come in from the top because it's too bulky and it's interacting with our five-membered ring. So it has to come in from the bottom, and that's perfectly fine. Comes in from the bottom, picks off the leaving group. Remember, once you add the alkyl halide and it regenerates the amine, the lithium has nothing else to complex to. So you form your imine. Now here's the part where I want to focus. Just like before, at carbon 2, R3 came in from the bottom. Just like before, R2 wedged and hydrogen dashed. The difference is that R1 and R2 are bonded through a ring structure. Okay. And so what I need to do is I need to rotate What do you mean I have to rotate? I can't have a wedge R2 and a straight on the plane R1, right? They all have to be on the same plane. So what do I mean by that? I am going to rotate, and I'll draw this slowly. And when I rotate, I want R2 on the plane so I can have everything and my entire ring on the plane of the page. If I rotate so that R2 is on the plane and phasing down, that means that my R3 group is now dash. So my structure actually looks as follows when I start introducing everything. Where the new substituent and the substituent on my SAMP are now anti or trans. So for cyclic systems, you are going to see the anti-trans product. And the reason for that is because your system or your ring is already locked into a specific form, into a specific configuration, right? And so it's harder to rotate things around. In this case, the reason we rotate it is because rings have to be on the plane. We want things on the plane, right? And if I need to bring R2 on the plane of the page, that means that my R3 group is rotating and has to be dashed, okay? It is probably the hardest methodology of the three to visualize, okay? Okay, part 4, removing SAMP and ramp. There are really just two methods to removing SAMP and ramp. So I'll use the simpler system that we started with. Okay. There are only two methods to remove it. The first one is probably the one we've seen before from Chem 124. Again, adding acid and water, where acid is your catalyst. And if you remember, it's just the complete opposite mechanism of adding the amine. You were taught both the forward and the backwards method. So again, if we use sulfuric acid as our catalyst, right? You regenerate your conjugate base. You add your water as your nucleophile. You do a proton transfer because you're trying to get rid of your SAMP. And you can already start seeing the precursor to your SAMP. So there goes my SAMP. There goes my precursor to my desired carbonyl compound, followed by bringing back my conjugate base to form my product. So that's method number one of removing my SAMP or RAMP. You've seen this again, second semester Chem 124. This is, despite the fact that this has been used before, commonly used, it's not the most popular because if other parts of your molecule are acid sensitive, then these reaction conditions are going to affect other parts and cause other reactions in different parts of your molecule. And so they're used, but they're not the most commonly used when you're trying to remove SAMP or RAMP. The second method is probably the most popular of the two. And so again, I'll just use what I made. And it's because it really doesn't affect a number of parts of your molecule, unless, of course, you have an alkene. But ozonolysis from Chem 24, you learned that it cleaves double bonds. And so what ends up happening is you treat this with ozone, and it simply cleaves your double bond to generate your carbonyl aldehyde. So most popular method number two. Okay. Okay, so now let me go ahead and introduce a total synthesis, and it's probably one of the most popular total synthesis highlighting SAMP and RAMP chemistry. Okay, the following is, excuse me, Zaragozic acid, and it's isolated from fungus. Okay. In 1995, Casey Nicolau from Scripps, excuse me, Research Institute in San Diego, California, completed the synthesis, or his research group completed the synthesis. Casey Nicolau is also known for being one of the first to synthesize Taxol, which is used in the treatment of cancer, and a number of cancer patients continue to take Taxol, and he was involved in this scandal where he had said that he had synthesized Taxol first, and it turned out that he wasn't the first one to synthesize, and it was a big deal in organic chemistry back in the 90s. Nevertheless, Casey Nicolau synthesized Zaragozic acid, excuse me, and you can find that in the Chemical European Journal, 1995. It is a pretty long read. But I just want to focus on the SAMP and RAMP methodology that he specifically used for this molecule. So let me introduce what the molecule looks like. And despite the fact that it looks pretty intimidating, we're not going to focus on the whole thing. Our part is pretty small, actually. Okay. So it's a pretty intimidating molecule. It is not the only total synthesis of Zaragozic acid, but it is probably one of the more popular ones because it was synthesized by Nick Casey Nicolau, who was in this huge scandal back in the 90s, early 2000s. So it's uh, it's a pretty referenced synthesis. We're only going to focus on this arm of the molecule. Okay. And so our target structure is simply that arm. And what he decided to do was he just flipped it over 180 degrees so that my ester part of the molecule is now on the left side. And if he flips it 180 degrees, the methyls are now dashed. Okay. This is our desired structure that he eventually couples to the rest of the ring. And he wants to make it from the following commercially available molecules. Again, this is a retrosynthesis arrow. He wants to make it from very simple molecules like propanol, SAMP, which is also commercially available now, and the following alkyl halide, which luckily is also commercially available. So this is our alkyl halide. And you can see that in this case, because he's already introducing this specific alkyl halide, one of the stereocenters is already introduced. It's already being bought. So all he really has to do is set this remaining stereocenter, and he does it with SAMP chemistry. And so let's go ahead and start this synthesis. Part number one. He starts with his propanol and SAMP. Under acidic conditions to form his imine. So that's part one. He introduces LDA to form his E-enolate. And so we'll do that as well. Oh, excuse me. And so there's my E-enolate. He introduces his alkyl halide that he purchases. And again, just like before, just like with Evans and Myers, oxazolidinone and pseudoephedrins, I'm just going to call this my RI, my alkyl halide. I don't want to worry about the stereochemistry and how to rotate things around. I'm trying to minimize the rotating and I'm trying to minimize the confusion. So I'm just going to add it as an alkyl halide. And so once I add it, you should always get the cis-syn product, right? And so there's my cis-syn product. Okay. I can rotate. And what I want to do is I want to rotate this so that my R group is where my methyl group is, and my methyl group is the one that is dash. So if I rotate so that my R group is on the plane of the page, it pushes my methyl group to the back. And there's my methyl group. I can then go ahead and replace my R group with the alkyl halide, with the alkyl group that it's representing. And you can see how it's coming together. I treat it with ozone and I form my desired aldehyde. Okay. Okay. Now we're not done, right? If you look at this specific aldehyde, this is not the target structure. We're nowhere near being done. If you look at your target structure, let me just copy and paste this. Okay. This is what I want. So I'll go ahead and number it. I'm missing carbon 1 and carbon 2. This is perfectly fine. Part 2. This is all Chem 124. And specifically, the next step is a Wittig, i.e. Horner, Wadsworth, Emmons reaction from Chem 124. And if you remember that the Wittig or the Horner-Wadsworth-Emmons reactions are specific to aldehydes and ketones. And they convert carbonyl compounds to alkene compounds. And so he takes the aldehyde that he just made, he treats it with a Wittig reagent. So this is the Wittig Wadsworth-Emmons reaction. And if you remember the mechanism of the reaction, you form your desired alkene. If you don't remember the mechanism, let me just remind you, it's pretty straightforward, hopefully. It goes through a three-membered ring, excuse me, a four-membered ring, intermediate. And I typically tell my students that the minute you form your four-membered ring, it collapses, and you should always form your phosphorus oxide, which is a salt, and it literally crashes out of your reaction if you've ever run a Wittig reaction. And you form your desired alkene, and your alkene product is always the trans alkene that is favored, which is perfect because that's exactly what we need. And there's my final product. Very nicely done using Chem 124 SAMP ramp chemistry to introduce one stereocenter, and that's it. Okay. Okay, so that's pretty much it for alpha alkylation. We are going to move on to aldol reactions in our next lecture, and we are going to see the return of David Evans oxazolidinones. Okay? Okay, you guys, that's it for this video.